Hi everybody, it's Miss Howell, and I'm going to do an equation review for the entire class. What I've done is I've taken equations from the AP Physics C equation sheet, and I'm just going to go through all of them. I recommend that you make your own note sheet. Doing that will help you study and help you organize the equations in your own mind. As I go through, I'll be talking about obviously what the equations mean, but then also the situations that we might see. So for starters, hopefully at this point, we are familiar with the ideas of position, which is labeled with an X and is always in meters. Velocity, which is defined as change in position over change in time. Change is always final value minus initial value. And then we have acceleration. And acceleration is change in velocity over change in time. Again, final minus initial. Now, we know that these deltas would work for algebra-based problems. For calculus-based problems, where we have a changing acceleration, we need to use derivatives to find velocity and acceleration. Let's remember that if I have a position time graph, that the initial position is the y-intercept and the slope is the velocity. And the area means nothing. Okay, if I have a velocity time graph, the initial, or the y-intercept is the initial velocity, which in algebra-based classes you'll see v sub I, and in calculus-based you'll see v sub O. The slope equals the acceleration, and the area means displacement. And so just a reminder that displacement is change in position. It's final position minus initial position. And then finally, for an acceleration time graph, well, we haven't really had to work with that too much. And these that I just drew here are not related to each other, but in this scenario, the acceleration would be changing. Let's see. The area under this graph would be change in velocity. Okay, then we've got our kinematic equations. Ideally, you can still write these out, and it is really useful, even on this calc-based test, to know the kinematics. This one is not listed on the AP equation sheet, this one that I just wrote. And the next one, these little X's here are just indicating that this is in the horizontal direction or in a single direction. So remember, we can't mix vertical and horizontal information in the same equation. The only thing that can cross between horizontal and vertical is time. So the way that we had written those was this. If you run into a good old-fashioned algebra-based kinematics problem, I sometimes find it easier to write it with the deltas. These up here are calc-based, and this Vx is an instantaneous value. And of course, we know that if we had a situation where velocity was changing, then the instantaneous slope would be tangent to the function at that point, and in fact, that would be a derivative. Okay, So then later on in the course, we learned about rotating systems, and we actually have the same equations for rotating systems. On the equation sheet, they only give you, I'm going to change colors to indicate that now we're into rotation. Okay, so on the equation sheet, they only give you one link between the linear quantity and the angular quantity. Remember that the word angular stands for rotating. And one way that I had helped us lay it out is to think about, kind of like we're thinking about position, velocity, and acceleration. Oh, I should add up here that displacement, I guess I said it down here, but displacement is change in position. Change is always final minus initial. So anyway, back to the rotational kinematics, we've got analogs to these quantities, and the analog of position is angle. And the way that we measure rotating systems is on the unit circle. So you learned about the unit circle in terms of degrees. Now we can also use radians. And so your position on the unit circle, like if I'm right there, that angular position on the unit circle would be pi over 4. Okay, so linear, angular, and this is measured in radians. Okay, so linear velocity corresponds to something called angular speed, and what this equation up here is saying is that if I take the angular quantity and multiply by the radius, I get the linear quantity. And then the same holds true for acceleration. Angular acceleration alpha, which is measured in radians per second squared. If you multiply that by the radius of a circle, you'll get the angular acceleration. This is meters per second. Meters per second squared. This is radians per second. Okay. So do I have enough room? I think I do. So I can take these equations and if I know them pretty well, and I do, then I can translate them into an angular version. So instead of x, I'm going to write theta equals 1/2 initial speed plus final speed times delta t. So there you go. So they're really the same equations. The ones on the left are linear. The ones on the right are angular. Okay. So we can use these equations to solve problems for rotating systems. All right. Next up, Newton's laws. When we first learned about Newton's laws, the first thing that I asked you to do is I asked you to draw a force diagram. And I think I had something like a book or a brick on a table. So I would represent the object as a rectangle. And then we've got the force of gravity, which by the way is mg. And we know that there's a normal force or a table force, a surface force acting up. Those two forces are equal and opposite. And they are called a force pair. The book, oh no, they're not called a force pair. I lied. Let me back up. Those two forces are equal and opposite because the book is at rest. So the forces are in equilibrium. Okay, so then we also looked at a situation where, let's see if I can do this in Notability. We looked at a scenario where we had an object that was sliding. I think I had like an air puck that was sliding at a constant speed. So if an air puck were sliding at a constant speed, let me go back. If there was no friction, the force diagrams would be the same. So constant velocity also gives us the forces in equilibrium. Okay, so when we talk about Newton's laws, I think I'm going to have to add a page here. Let's see if I can figure that out. Yeah. Okay, so when we look at Newton's laws, what we're really looking at is the difference between accelerating and non-accelerating systems. So Newton's first law says, okay, so that's Newton's first law, and I don't think there's any emotion in it. What I meant was in motion. Okay, so first he's setting up this difference between, or he's grouping together objects at rest and at constant velocity. And he's separating them from things that are accelerating. Okay, then for his second law, for Newton's second law, so this is the first one. Let me go back. There we go. So the second law is F net equals ma. So now he tells us if there is a net force, what happens to that mass. And then Newton's third law is about force pairs. And a lot of people will state this law as for every action there is an equal and opposite reaction. And that's really, in my opinion, in the modern world, a terrible way to state it. What they really mean is the force of object 1 on object 2 is equal and opposite to the force of object 2 on object 1. So I think in class we did a couple of examples where we had like a spring scale, and I had one person pulling on this side, and I had another person pulling on this side. And if the spring scale is not moving, then the pull on the left would be equal, but opposite direction as the pull on the right. I mean, it would have to be that way, right? If this is not going to move. So that's all Newton's third law says, but it turns out to be super, super, super helpful. Okay, so those were Newton's three laws. So now back to this. So when we were drawing these force diagrams, the first thing that I did was I put what's called the center of mass, COM or CM, and that's what this is. This is the formula for the center of mass. We did some problems where you had a number line. And the number line defines position. And then you had different masses along that number line. And you could determine center of mass by taking each mass times its position on the number line, adding them all together, and then dividing by the total amount of mass. Okay, so center of mass turns out to be important in a number of different situations. This next one, there's Newton's second law, stated in terms of acceleration. One thing that's kind of nice about doing it this way is when you think about gravity, G, or 9.81, is equal to the weight of an object over its mass. And this is actually how we define gravitational field strength. And gravity is not on the exam for this year. I think it's in Unit 7 of the AP the AP syllabus. But it's, we want to learn things for the sake of learning them, right? Okay. And by the way, the gravitational field strength would be different in different places. Like on the moon, for example, it's about 1/6 of Earth, so it's roughly about 1.67. And when people write gravitational field strength this way, they don't write meters per second squared. They write newtons per kilogram. And a Newton per kilogram is the same thing as a meter per second squared. In fact, it's kind of handy. This would be a good thing to review briefly as well. If F equals ma, mass is measured in kilograms, and A is measured in meters per second squared, then a Newton is a kilogram meter per second squared. Okay, let's see. I think I'm going to add another page because what I'd like to do next is talk about friction, but also talk about all the different kinds of forces that we studied. What I called Unit 4, and the College Board I think calls Unit 2, is all about forces. So let me add a page here. Let me see if this will move. Okay, so forces. So what kinds of forces did we learn about? So the first one that we all know and love is the force of gravity, and it's equal to the mass of an object times g. G is equal to, of course, 9.81 meters per second squared on Earth. Okay, let's suppose we have an object sitting on a table. We already reviewed Fg and Fn. We want to remember that this is an idealized situation. Sorry, I'm just shutting the window because of the barking dog across the street. Okay, so we've got Fg and Fn, and Fn is called the normal force. Be careful that you don't call it the natural force or some other n word that starts with n. Normal force. Normal, the word normal means perpendicular. And the normal force always acts perpendicular to the surface. That's the definition of a normal force. So to have a normal force, you must have a surface. Right now, I'm sitting in a chair. I've been sitting in it since about 7:30 this morning. It is now 5:24. Oh my gosh, I need to go outside. But yes, I can feel the surface of the chair pushing up on me. Okay, what if somebody comes along and this book is sitting on the table and somebody pushes it? We would probably call that FA for applied force. So forces in general are a push or a pull, but that's kind of your generic added force. And then what if somebody pushes it at a constant speed? If they're pushing it at a constant speed, then the forces must be in equilibrium, and Fk is the force of kinetic friction. And the equation, which I lost, there it is. Let me just snip that real quick. Let's talk about these absolute value signs. Yeah. Okay, so they're putting these absolute value signs on here because we're interested in the amount. And remember, there's this idea that we can break friction. So like I'm pushing on the side of my iPad right now, and the iPad's not sliding yet. So I can push up to a point, and that point is defined by the coefficient of friction times the normal force. The absolute value signs are indicating that I just put the amount. I don't need to worry about direction. But let's talk about direction of friction. Well, first let's talk about the two types of friction. So kinetic friction is the friction to keep it moving, keep something moving. And then we've also got static friction. This FF, it's either one. It doesn't matter. The force of static friction is the force to get it moving, which is, the force to get moving. And the definition of friction, like the normal force acted perpendicular to the surface, the force of static friction acts parallel. Ooh, wow. Parallel to the surface. And it always opposes motion. So looking back at this diagram, I can see that this force of kinetic friction here, which I'll just darken so you can see what I'm talking about, is acting parallel to the surface and it's opposing the motion. So presumably this object is moving to the right. Okay, other kinds of forces. Sometimes we had a tension force. The College Board sometimes likes to just call it a big T for tension. There's not a lot, but there's some variability in what people label things, but the concept of tension is the same everywhere. Tension is when you pull, it's always a pulling force. If you've ever tried to push a rope or something, you can't really push a rope, right? You can pull on a rope, but a tension force is a pulling force on a rope, a cable, a chain, a string. Hopefully you get the idea. A long, thin, flexible thing that you use to pull something along. So that's tension. Okay, all about forces. Great. Let's go back. Okay, we covered Newton's laws. We covered those things. Okay, so now let's look at what happens with rotation. So in rotation, we have to do a couple of things. We actually have to redefine force and we have to redefine mass. So let's suppose that I have an object. There it is. And my object has some mass, but now the mass is going to be traveling around a circular path. And we studied all kinds of different scenarios for this. It could be a ball on a string. It could be somebody going around a corner in their car, okay? And what we know is that the radius matters, right? If you try to make a corner with a smaller radius, you need more force to make that happen. And so we know that radius matters. Another thing that we know is that the distribution of that mass matters. So this value here is called moment of inertia. And it's the distribution of mass around a pivot. I have a couple of explainer videos on how to do an integral of moment of inertia for like a thin rod. And I could do a couple more if you like. The algebra definition is just the sum of mr squared. So if I had this figure here, the moment of inertia of this figure here would be m capital R squared plus m little r squared. So basically I'm just taking each mass times its distance to the pivot point and adding them together. Okay, so let's see. We've got moment of inertia. We've got this idea that radius matters. Okay, so what's this thing here? So this, let's say that I have an object like well, it could be, let me try this again. We did a lot with meter sticks, so I'll take you, but I wanted to make a nice rectangle for me. There we go. Okay, let's say this is a meter stick. Let's say the meter stick is fixed at one end and you want to rotate the meter stick. Okay, in order to rotate the meter stick, you have to exert a force. But it matters where you exert the force, right? You're going to get the most bang for your buck exerting it at the end. So that force is a vector, and I really shouldn't probably draw a curved line, because actually your force has a direction like that. And it has a distance from the pivot, which I'm going to call R. And then you'll see this torque equation. Torque equals R crossed with F. Now, if you go back to our notes, or if you think about what we had talked about, this angle matters. So like if I did push on this meter stick at an angle, only the perpendicular component would count. And the perpendicular component would be, if I measure the angle here, perpendicular component would be F sine theta. If you have learned about cross products, and they are listed on the equation sheet, this cross product is indicating that you take these two values, FR, and then you multiply by the sine of the angle between them. Okay, so that is how we compute torque. The force times the distance from the pivot times the sine of the angle between them. So notice I measured the angle between the force and the radius. Okay, so once you have taken force and done some fancy footwork to convert it into a rotational value, and once you have taken mass and done some fancy footwork to turn that into a rotational value, now what we can do is take Newton's second law and apply it to a rotating system. And that's what this is here. So before we had, I'm going to just switch colors. Before we had F net equals MA. That was the linear version. Now our rotational analog is that net torque is going to create an angular acceleration around or of a distribution of mass around a pivot. Okay, moving on. Let's see. Okay, let's move on to energy, work, and power. We started out with the definition of work. Work, if you learn the definition of work like in elementary school, work is just force times distance. And the force and the distance have to be in the same direction. Now that you're not in elementary school, you'll see that work is a little fancier than that. It's the integral of the force dot dr, where r is still going to be the distance added up over the limits of your integral. This is also a vector product. This dot stands for cosine. Or if I were teaching an algebra-based course, I would say FD cosine theta. So let's look at an example of that. If I have a suitcase and I pull on it with a force like that, and the force is not parallel to the distance that I travel. So there's my theta, and I move the suitcase this distance. The work that I do, when I calculate the work that I do, I can only use the parallel component of my force. And that parallel component is F cosine theta, right? That's the, if you think about this right triangle, that's the adjacent side. So that's the dealio with work. If you think about what happens with work done by friction, let's say it's a scenario where, okay, I've got my good old standard book on table. So I've got FG, I've got FN. Now I'm going to pull the book on the table, and I'm going to pull it with a constant applied force. So you can imagine, there I'm pushing my iPad with a constant speed, okay? And in order to push it at a constant speed, there must be a frictional force. If I push the iPad to the right, so I push it that way, then my force of friction and my distance are in opposite directions. So the work that I do is actually negative. And in some of the practice problems on the AP Classroom website, you'll see that negative FD for work done by friction. Okay. What else do I want to say? Oh, I have also seen questions where, let's talk about this integral stuff. Here's where they like to put that. What if I had a graph and it had force and it had distance? And what if the force was changing as a function of the distance? One situation that we saw that in was a spring. Well, we actually used X, I guess, with a spring. And in that case, we know that the area under there would be the integral. When we learned about this in class, we were still I was still in algebra mode with you all, and I talked about how this point would have a height of kx. So to get to this point here, I would go over x and I would go up kx, and the area of that triangle is 1/2 kx squared, and that is the energy stored in a spring. But we also know, now that we know our calculus so well, that the integral of kx is 1/2 kx squared. So check that out. So that's this. If this negative here, by the way, refers to the spring itself. So the spring force is up, and it's opposite to the direction of the change in stretch. So that's why there's a negative there, to account for that situation. Okay, I think I'm going to need some more space. So what am I going to do? I'm going to add a new page. And I'm going to take my equations with me. Yeah. There I am. Okay. So we've got these ideas of work, and then the next idea is, well, what do you do with work? Well, you can use work can be converted into other forms. What is work measured in? Do you remember? Work is measured in joules. So if I go back to my definition here, work is a Newton times a meter, and that is a joule. Not to be confused with, going back to torque. Torque is force times distance, or force crossed with distance. This is a Newton meter, which you cannot say is a joule because it's only for the specific rotational situation. It's a little confusing. I know. It's something you got to know and remember. Okay, back to here. So work can be converted to energy. And energy is the ability to do work. So I could push on something and make it go. I could push on a wagon and make it go. And if I did that, the push would be force times distance, and I would give it kinetic energy. So you can say work is equal to a change in kinetic energy. And kinetic energy is defined as 1/2 mv squared. This is a scalar quantity, no vectors, and so solving problems with work and energy can be really, really great. Another kind of energy that I'll just write this down, kinetic. Okay, so this is energy of motion. So it's due to velocity. Okay, another kind of energy would be energy due to position in the gravitational field. So I lift a ball and I drop it. When I lift it, I give it gravitational potential energy, and that's just mgh. And when you think about this, this is really just Fg, and this is really just a distance. Oops, getting my R's and D's mixed up. Not that it matters that much. But anyway, here you can literally see the work that you do to lift an object is stored as gravitational potential energy. Now, we did look at, we did a bunch of problems where you take an object and you drop it. That was kind of fun. And in that case, the gravitational potential energy at the top equals the kinetic energy of the ball at the bottom. So then we would say change in gravitational potential energy equals the kinetic energy, mgh. I would say delta h because it's really this difference. It's not like, it's the difference between those two positions. Equals 1/2 mv squared, and mass canceled, and we solved this for v equals the square root of 2gh. That was a handy equation. It's also, this equation is the same as this one. Boom. Okay, the last two equations here are the definition of power. So power is just the rate. Power is a rate of doing work. So it's energy over time. So you can think of a situation where what if we had energy and time in a graph? Power would be the slope, right? Rise over run, boom. This is another way to compute, one more thing about power. Power, it could be energy over time, or change in energy over change in time. It also could be change in work over change in time, because energy and work are equivalent. And remember, energy just changes form. It's neither created nor destroyed. Sometimes energy is kind of wasted, like in friction, but it doesn't just disappear. Okay, and then, back to power, and I'm running out of room for myself here. Sorry, folks. Power is energy over time, or work over time. Work is force times distance. Distance over time is velocity. So it turns out that power equals force times velocity. That's what this is saying. This is a kind of a sneaky way to find work. Notice there's a dot again, just like there was before. It's only the parallel component that matters, just like in the work equation. So you could write this as FV cosine theta. That's what that dot means. Okay. So we're getting there, folks. We're really getting there, I promise. So how does that relate back to the rotational stuff? So rotational kinetic energy is the only one of these that really matters, and we have the definition of rotational kinetic energy is 1/2 I omega squared. And again, I is moment of inertia. And omega is angular speed. Now, I'd like to do an example of something that I saw. It's actually one of the AP practice problems, and I should really make an explainer video for that too. But as long as I'm here and I'm running out of time to make explainer videos, I want to remind you of something. Let's say you have a ball, or really any round object rolling down a ramp, and the ramp has height h, and it has mass m. Okay, the ball has gravitational potential energy. And that gravitational potential energy is going to turn into two kinds of energy. It's going to turn into translational kinetic energy, which is basically like sliding motion. The ball doesn't slide, but the center of gravity certainly does appear to slide or translate down the ramp, right? Then you also have rotational kinetic energy because the ball rotates. So, you can set this up. mgh equals 1/2 mv squared. That's what we were setting up. I lost it somewhere. Oh yeah, down here. That's just if something were just sliding, then you'd be good there. But this is not sliding, it's rolling. So there's also rotational kinetic energy, which is 1/2 1/2 I omega squared. Let's say that this is a hoop, because that's all I can remember right now. The moment of inertia for a hoop is 1/2 mr. Nope, it's not. It's just mr squared. Goodness gracious. And I'm really playing fast and loose with my M's here, you guys. I'm so sorry. I've got capital M's, I've got lowercase m's. It's all the same M, okay? Okay, so what I'm going to do is I'm going to take this moment of inertia for a hoop, and I'm going to plug it in right there. So I get mgh equals 1/2 mv squared plus 1/2 mr squared omega squared. All right, I'm going to add another page here this is so cool. Until it doesn't work. I broke it. Where's page 7? Come on, Notability. All right, well, I guess I can't write on the invisible page, so we'll just keep going here. Now, remember that r times omega equals v. This is what relates angular speed to linear speed. So this is just v squared. So check it out. We have mgh equals 1/2 mv squared plus 1/2 mv squared. I really wish that page would have showed up. Oh, it's there. Okay. I put it in the wrong spot. The plot thickens. Let's see. There we go. All right, I'm doing it. Okay. So again, mgh equals 1/2 mv squared plus 1/2 mv squared. So mgh equals just mv squared. So the m's cancel, and v would just be the square root of gh for that hoop. And remember, depending on the shape, like if it was a solid disc, for example, the moment of inertia is 1/2 mr squared. You would plug in a different value for I and get a different number right there. So that's a really common type of problem. Something rolls down a ramp, how fast is it going at the bottom? And you need to use this technique to solve it. Okay, let's see. Let's look at the we're on the last page. Our last topics, momentum and impulse. Okay, so first of all, the definition of momentum is just mass times velocity. And the arrow means that it is a vector. Momentum has direction. There are some equations that we talked about for linear situations. So for example, in an algebra-based class, they really love this stuff. You got one cart, it's moving along and it's going to hit a second cart. And they might hit, well, they're definitely going to hit each other. They might stick together, they might not. Let's say they stick together. They're going to go slower, right? This one has a mass. This one has a different mass. This one has the sum of the masses. The idea about momentum is that momentum is conserved. And what I mean by conserved is equal. The momentum before equals the momentum after. So in this scenario, the momentum of the first cart would be m times vi. The momentum of the second cart would be m times 0. It's not moving. And so that's 0. And the momentum of the carts stuck together would be little m plus big M times Vf. So this is called an inelastic collision. You can also think about a situation where we have an elastic collision. In an elastic collision, the first cart hits the second cart and makes it go. And we would say the mass of cart 1 times its initial velocity plus the mass of cart 2 times its initial velocity equals the mass of cart 1 times its final velocity plus the mass of cart 2 times its final velocity. So again, we're just saying take the momentums on both sides of the equation. They must be the same because momentum is conserved. And this is an elastic collision. Okay. I'm gonna kind of sidebar this for a minute. We'll come back to angular momentum in just a minute. So then we talked about the impulse momentum theorem. And the impulse momentum theorem says that the impulse on an object equals the change in momentum. Now, impulse is force times change in time, and delta P is equal to mass times change in velocity. Remember also that change is final minus initial. So actually I saw this on, let's see if this, I need more paper. 1 second. So one thing that I saw on one of the practice questions was a graph like this. So what could that possibly give you? Force divided by time doesn't mean anything, but force times time is impulse. So, here the area equals the impulse. J is the unit for the impulse. The units for impulse are Newton seconds, and the units for momentum are kilogram meter per second. These two things are equivalent because, as you may recall, a Newton is a kilogram meter per second squared, and when you multiply that by a second, you get a kilogram meter per second. So this equation here, this one, this integral, again, is trying to tell you that the area under a force versus time graph gives you the impulse and therefore the change in momentum. And really, when you look at this formula, it's just a rearrangement of the same idea, right? So, okay, where was I? Okay, so for angular momentum again refers to a rotating object. Our symbol for angular momentum is L. Angular momentum is okay, come on, brain. Let's start here. Is equal to the moment of inertia times the angular speed. Wow, I'm losing the ability to write. Okay, there we go. Times the angular speed. And remember that angular momentum is conserved as well. So we had done, we remember we did a lab where there were kids on a merry-go-round, and I had them, they went in toward the center, and the merry-go-round sped up. And so what we know if the kids started on the outside, what happened when they moved to the inside? What happens to their moment of inertia? Their moment of inertia goes down because they're getting closer to the center. And if their moment of inertia goes, oh my goodness, that's speed. Come on, Howell. Their moment of inertia goes down. If their moment of inertia goes down, then they speed up. The merry-go-round sped up when the kids pulled themselves toward the center. And you can see figure skaters do that. They pull their arms in and they speed up. So yeah, that's a really helpful type of thing. This formula here, this is a cross product. This is actually saying that the angular momentum of the of an object that is spinning is, the cross means that it's actually through the axis of rotation. So if I had a bicycle wheel and it was, I'm just going to think about one particle on the wheel for a moment. At any given instant in time, that there's a little particle which has some mass, and at any given instant it has some momentum, and it has a radius from the center. And what a cross product means is that the momentum is actually along the z-axis. So that's what this is trying to tell you. And you may remember that I had a bicycle wheel in the classroom, and I would spin it and kind of hold it up like a magic trick. And it was because this angular momentum was actually along the z-axis along the axis of the wheel itself. Okay, I think this video is plenty long. I'm going to just say that these equations here are for simple harmonic motion. This has to do with period and frequency. Period is, well, this one actually might come in handy. Period is the time for one revolution. And frequency is revolutions per time. So period and frequency are reciprocals of each other, which you can see there. These next two equations are, this is the period of a pendulum. And this one's for a mass spring system. I have some videos on my YouTube channel of me jumping on a trampoline, which is basically a mass spring system. And what this is saying is if you increase the mass, you lower the period. So the heavier the thing is. I don't know if you've ever been to a playground where they have those things with a big spring, and a kid sits on it and it goes back and forth like wah, 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 wah. If you increase the mass, you will increase the period. These two equations, well, this one we did learn, but they took gravitation off the exam, so I'm just going to leave that for now. All right, I hope this was helpful. That was a lot. Please reach out to me with your questions. Yeah, and I'll have to think about, wow, my handwriting got a lot worse as I went through here. I'll have to think about making some examples to go along with this. But for now, try to get your notes organized in one place. Thanks very much and good luck.